Today, it is where we'll begin our journey into model assessment. Think of this as like learning how to become a student who is taking a test to a grader. So you need to know what's the rubric for the test. So how do we know if a predictive model is doing its job well or is it not doing its job well? Whether it is about like focusing whether stock price or even just predicting who might win the next basketball game, we need reliable ways to check this model. So today we'll learn some tools to uh, see that like if data science are like actually doing something great or are their model just like useless. So um, in today's lesson, you need to imagine that your math teacher is always predicting your test score. So how do you know that your teacher is doing a great job? This is today's content. So we'll first go through the guidelines for it's like a report card for models. And then we will find some like quantitative analysis for it, which is the actual grades that a model might get. And then we need to compare some models. And then we'll see sensitivity analysis. So the first part is a guideline. So how do we assess a model if it's good or not? First, need to see that if it's doing predictive performance, which means that how reliable does the model seem. So can it predict future events accurately, like a weather model that actually knows when it rains? And validity makes sense real world. How valid are the model's assumptions? How well does it fit into the real world phenomena? And then the robustness, can it handle messy real world data, or it can just handle edge cases? And then interpretability, how well can the model be understood and justified? So can human understand reasoning, or it's just like too theoretical and not really sensible or reasonable for human being? And we'll go through these things one by one. The first criteria is accuracy and precision. So um, we can think of like building a model as archery. So we can look at the graphs, um, accurate but imprecise. It can also be precise but inaccurate. But a good model needs to be accurate at the same time. But in general, it's harder to judge. We can see that the first graph is accurate but not precise. So we're all targeting here, but we have a wide range of data. However, the second one, we have a small range of data, which means it's very precise, but it is at the target, so it's not accurate. So if you have any like question, um, just say anything you yeah. And the other thing is about um, uh, interpretability. So um, clear explanations matter more than simple. Uh, uh, that's a very important thing. And the logical relationship clear, make sure and each part of the model can explain, and all mathematical statements have physical meanings, and all variable represents substantial real world parameters. And next, we know to have generalizability, which you question our models based on these 5 cents. Can the model be extended beyond its intended problem? Is the generalization easy to conduct? Does generalization make physical sense? Are the generalized model as optimal as the origin? Or can it be applied to relevant databases? These are all things we need to consider. So we can give out some example. For example, we can think of that can we generalize this across population? So these are something we can think about. Sorry. Or can it be generalized over time? And other related tests that have the same systematic comments. So we can think of in this ways. And the last thing is efficiency. So we need to think about that. Is the model computational efficient? So we do not need to waste a lot of electricity and computational power to run it. And has the model structure been streamlined for understanding? Which means that we need to just like understand it in a fluent way, but not just like to move from one place to another in a not reasonable way. And then is the model compact or concise? How hard to make revisions? And is it effectively scalable? So what means computational efficiency? Can we run the model on a smartphone in seconds, or we need a supercomputer to run for hours? Scalability means that can it handle 10 times more data without slowing down, or we cannot? So, but there are some trade-off in this four criteria. So you need to think about it, whether which criteria you want to maximize and which one can be forgotten for a second. So complex models like deep learning can be very accurate, but it might be less efficient. However, simple models like linear regression can be efficient, but sometimes it's just too basic. So you need to like think about it. So we'll do some quantitative analysis. Yes. Do anyone has any question? Or,
Which accuracy more important or precision? Accuracy or precision?
sorry, can you repeat
What's more
again?
important, accuracy or precision?
These two are both important, but in terms of mathematical modeling and like I'm fancy, I would say that accuracy will be more important. And if you get more precise, then it's a bonus point. But I think accuracy must be prioritized in those like modeling competitions. Yeah. So another part will do some quantitative analysis. So we'll first talk about residual analysis. So what is residual? It is the difference between predicted and actual values. Let's give an example. Like the actual value is 10 and your predicted value is 8. So how to calculate the residual? Which is E. So it's Y minus the predicted value, which is 2. So this is how we calculate it. And there are different types of residual. And just like not all mistakes are equal. So we need to have special ways to measure this difference. The first one is standardized residual. These are adjust residuals by how spread out our error techniques are. It's like saying that this error is 2 standard deviations away. So there are different formulas to calculate, but I'm not going to expand on that. If you're interested, you can search it in the internet. And the second, studentized residual. So this go further by accounting for how influential each data point is. So which means that some mistakes matters more than others. The third one is Pearson's residual, which means that which are like common in the data where we try to categorize something. So categorical data, and they compare observed and expected counts. So the formula is this one. And I'm not going to elaborate. Yeah. You can like search it or think about why is it good or not. So this residual plots can be generated and analyzed for model assessment. So we can think about if the residual is very big. For example, we have a residual like 5, so it's not very good. I need to think about which kind of residual it is, and then how can we improve it. For example, when get one set of data, which is like our actual value is 10, 8, and 6, but our predicted value is 12, 10, and 8. We can see that there's a systematic residual of 12. So can we just minus 12 by our like predicted value so we can have accurate one? So this is just for standardized residual, but we have different methods for different ones. So this is an example of calculating residual using Python, and you can just check it with internet, and just like it's just a very simple one. So yeah, I think like you can just figure out yourself. And usually when we're thinking about calculating it, we will do something called standardization, which means that we will change our residual into residual divided by the standard deviation. So this is where how we standardize it um, to not allow some extreme circumstances to happen. Yeah. So the second technical term is R square and adjusted R square. So this is the original version of it. And we'll talk about the improved one later. So what is R square? R square measures how much variance the model explains. So if the R square is 0%, then your model is no better than guessing the mean. But if it's so it's very bad if it's like 0%, it means that it's not really relevant to your model. So if it's 100%, it means that the model is a perfect fit for the data, which means that which shows like it's almost always overfitting. Overfitting means that you put a too big stress on some specific data, which is not good. So a good R square will be in between 0 and 1. So like if it's like 0.7, 0.8 something, it's very good. And you can fluctuate around as long as it is in a reasonable span. Yeah. However, we have some very bad thing happening. So this is the macro expression for R square. Yeah, so you can see that is a criteria. If it's like 0.5 plus-ish, it's very effective. However, there is a limitation, which means that if we add some useless predictors, it will always increase R square, which is not good because we want R square to be objective measurement of our model. But if just by adding some useless thing, we can increase R square, it's not really objective. So this is the updated version. It is called adjusted R square. So this is the updated one. So why do we call it adjusted R square? Because we adjust the original R square to penalize adding unnecessary predictors, just like useless predictors. So this will prevent the problem of overfitting, which I explained a moment ago, means putting too much stress on a small range of data. So this is the formula. You can try to think about why it works. So in this case, n is the number of data points, and k is the number of predictors. Yeah. And this is a Python program to calculate R square. Yes. So how can we compare our R square and adjust R square? So we can think about there's like pros and cons of both. For R squared, it's very simple and has simple interpretation, and the formula makes very much sense in real world. However, it always increase with more x. So when we think about if we have this much data, so this is data we're trying to do something with, if we can just use this like y equals bx to fit the data, the R square will be very big because you can see that this is the predicted value and this is the real value. So we need to find a difference in it, and it will be really, really big. However, if we have like y equals ax to the 5 plus bx to 4 and so on and so forth, we can have something like this, and this will largely decrease the like loss or like R square. So we can see that you can now think about like predictors or factors just as like the number of x, but it actually means a different thing. But you can think of like that because it's easy to memorize, and you can show why like adjusted R square is not good. R square is not good. So for adjusted R square, the pros is that it controls overfitting. However, it is much harder to explain. Yeah. So we'll go on. So then I will introduce some model comparison techniques. There are basically two of them. The first one is AIC. The second one is F-test. We'll introduce them both. It is about how, if we have two models, models A and model B, how can we see which one is better? So we'll choose the one that's better to be used. So the first one, AIC, stands for this one, which I'm not going to say out. So AIC is a statistical matrix used for model selection. It estimates the relative quality of models by balancing two things. The first one is goodness of fit, which means like how well the model explains the data. And the second one, model complexity, which is the number of parameters used. So this one is basically based on these two criteria, and it is trying to get it is a metrics used to evaluate the model. So the key idea is that AIC helps choose model that generalize well, avoiding both underfeeding, too simple, which means too simple, and overfeeding, which means too complex. And if the AIC value is low, and this indicates that the model is good, and vice versa. So the mathematical formula is basically this, where K is the number of estimated parameters in the model, and L hat is the maximum value of the model's likelihood function. So it's measuring the feed quality. This one, and this one is like measuring this one. You can just like see how it's going to do. So we can just break down the formula a little bit. This part is measuring how well the model fits the data, as we said before. So if the fit is better, then we'll have a higher likelihood, which means a smaller term. So this one will be higher if the model fits well, so which makes this smaller, so it aligns with the things I said before. And for this part, I'll choose another color. If there are more variables, more parameters, then we'll have higher penalty because k will be bigger, which makes this bigger, which is not the things we want. So it encourages simplicity. This is a larger chain of this model or the status criteria. So why should we use AIC? Because we can use it for model comparison, and even if we have multiple models, we can find the one with the lowest AIC, which will be preferred. So we can compare like linear model and polynomial regression for the same data set. And we have like a trade-off resolution, which I said before, it automatically balances underfeeding and overfeeding. And yeah, however, there are some limitations of it, but it's not a very big problem actually. So actually, AIC assumes large sample size, which means that you need to have a lot of data in order to make AIC efficient. However, if we only have small data set, we can use corrected AIC. And I'm not going to explain further. If you are interested, you can search it in the internet. So this is another correction. The last one we mentioned is R square and adjusted R square. Yeah. So this is one of the things I use. So there are some Python things you can learn and some programming package that have formula in it. You can just like use it if you need. Yeah. So we have another one. This one is called F-test. So F-test is a thing that compares two things as well. The first one is the variance of two samples. And the second one is the goodness of fit that we mentioned earlier. So what does the first one mean? It means that we need to check that if the two groups have equal variance. And this is the prerequisite for t-test. And the fit of goodness of fit. So it is about if a complex model significantly outperforms a simple one, as we mentioned earlier. Just like it's about a regression analysis again. Yes. So the mathematical expression is basically this. It's very simple, but actually when you break it down, it's kind of complex, and you can like learn it if you want. And I'm not going to elaborate further. So there are a lot of step-by-step procedure for conducting F-tests. So we first need to have hypothesis. This is the steps. The first one is to state hypothesis. We can have hypothesis 0, which means like simple model is accurate. We always have simple model is accurate as the hypothesis 0 because this is the one we like. Simple models are sometimes greater. So H1, hypothesis 1, is that complex model is significantly better. So we need to reject H0 in order for us to choose H1. So we need to first check if this is right. So for step 2, we will compute F statistic both. So we'll fit both model and just like use this kind of formula to use it, and then we'll determine the significance. So this is F-test is used for comparing a simple model and a complex model. So if our P is smaller than 0.5, we reject H0 and vice versa. So if our calculated P is smaller than 0.05, we don't use H0. So we will think the complex model is better. However, if P is greater or equal to 0.05, we will use the simple model. And this is one of the like Python we use to calculate the things. Yeah. And for the last part, we'll talk about sensitivity analysis. What is sensitivity analysis? It's basically ask how fragile our model is. So how to see? So what is sensitivity? Sensitivity usually happens when we have an X and we have an Y. We need to think about how much X we need to change in order to have a significant change in Y. So we're thinking about like if we're building a model and then if the age of the child like grow up by 1 and the like consequence or the like output of the model change significantly. This is a big problem because we want things to be kind of reasonable and do not change over time. So we do use sensitivity analysis. So what is the process? The first one is one at a time. So we first need to choose one input variable and keep other variables at their baseline value and constant. And we change the designated value variable, that's the one, in smaller increments. And then we see how much like y are we changing. So there's an x before, there's an y before. Y is the output of x. And we change x a little bit and we see how much this was very small in order to test. And if y changed by a big sense, this is not good. But if it's changed by a small sense, it's very good. It means that it's sensible. So using this example, I think we can see what is a sensitive analysis. It quantifies the range of uncertainties in input parameters. It identifies a target output to analyze, and then runs model multiple times using input parameters. And using this output, we calculate sensitivity of the desired parameters. So one at a time, I think I have to make it clear. Maybe I have the slide put it here. Yeah. So we can first like think of x1, and then for the second one, we consider x2. X1, x2 are all the input variables, and y is the output. We need to consider all the input variables until we have no more. So we can, if all the like input variables are robust, so it does not, so y does not change very much with a small change in x. So the model is robust. And there's another method to calculate sensitivity. So it's called derivative-based approximation, and it quantifies how much is the input parameter affect model's output. So it's always how much x we need to change in order to have a big change in y. So how to do that? We move from x to x plus delta x, and then we're holding other variable constants, and we still first the change in fx, which is 1. So the basic logic is always the same, but the formula is really different. So delta f, so this is the formula, which nearly equals to, so we can see that this is the change in output, which is delta y. And how do we calculate that? It is the change in delta x times the derivative of the function between y and x. So for example, when you consider that if y equals 4x, then this one will be 4. So we can see that the change in y is just 4 times change in x, which is kind of reasonable, but you need to like evaluate by your own sense, because like this is quite subjective. So what do we need it? Because it gives us mathematical bounds for output fluctuations, and it works first. It only works for restricted domain, because if we want to find a derivative, we need to have a restricted domain, which makes very much sense, and it is useful for experimental analysis. And this is how it's a perfect example for COVID-19 model. So we just like use the thing we talked about a moment ago. Yeah. So this is basically what we're covering today. And if you have any question, I feel to ask. Yes, it's over. Yeah.
Yeah, thank you so much for doing that. Do we stop the recording?